Welcome to AGU 24.
Welcome to AGU 24.
Welcome to AGU 24.
Last month was the American Geophysical Union, or AGU, annual meeting. This is one of the largest gatherings of Earth and space scientists, and I got to present my own research and catch up with friends, but my favorite part about this meeting was getting to see so many amazing research projects that are making incredible discoveries and progress in the geosciences. So this video is a compilation of poster presentations from this conference. And I wanted to make this video for a few reasons. One, to showcase the variety of research that's being done in the geosciences right now that anyone can go into if you're interested. Two, to showcase the diversity of researchers doing this work. And three, to provide a peek behind the curtain of scientific conferences for those that maybe haven't attended yet, but maybe they want to in the future, or maybe they're presenting their work at a conference soon. This may help give you an idea of what to expect for poster presentations. So let's get into the poster presentations. I did put chapters in this video so you can scroll along the bottom to see which topics you want to jump to if you don't want to watch them all. And with that, we're going to start with the first one, which I'm sure will be a fan favorite. You probably know them as Diconite on Instagram. It was hard to even film this presentation because they had so many people trying to come see their poster. So here is a very short summary or overview of their poster that showcases their research on the link between deglaciation and volcanism in Iceland.
Okay, I am researching the Tungarhorn lava flows in Iceland, which erupted during and following the most recent deglaciation in Iceland. And the reason why I am so interested in these flows is there's a known relationship between deglaciation and increases in volcanic activity. Fully constraining this relationship is very important for the future of studying volcanic hazards. A lot of areas of the globe are undergoing mass deglaciation, so knowing what kind of changes and eruptive breaks in activity that could eventually lead to is very important for volcanic hazards and safety.
Next, we have Bethany, who is looking at factors that affect soil hydrological processes, in other words, water processes and soil, and how this affects water availability as a whole.
Hi, I'm Bethany, and I'm studying how juniper encroachment affects how water moves through soil. So juniper encroachment is happening in the sagebrush steppe in the west, and what's happening is juniper trees are growing in sagebrush ecosystems, and the roots are different, so we expect that the way that water flows along these roots is different depending on which type of vegetation it's under. So we have sites underneath sagebrush and junipers, and what we want to find out is how the soil moisture varies. So down here we have precipitation, and we can see that juniper reacts much quicker and decreases much more rapidly than sagebrush does, which kind of increases and then stays pretty constant. So we wanted to calculate the soil water velocity, and what we found was that sagebrush actually has a greater soil water velocity, so the water moves through the soil profile much faster, the average moves faster than the junipers. We're not really sure why it does that, so we're going to keep studying this. But yeah.
Awesome. And why does this matter to, just an average Joe on the street?
Yeah, water availability is super important. There's a lot of agriculture that happens on this land, and so it's important to understand how as this juniper continues to encroach, what that means for water availability to the west.
Next, we have my good friend Kat from UTEP, who is doing some amazing work along with many other UTEP collaborators to bring their local community into conversations surrounding research so that the science that they're working on aligns with community goals and the needs of the community as well.
Hi, so I'm Catalina Salas. I'm at the University of Texas at El Paso, and today I'm presenting my work with the CLOG project on mentoring. So CLOG is a really cool word, community-driven inclusive excellence and leadership opportunities in the geoscience. And what it is this amazing program that is connecting graduate students and postdocs to the community, but also making sure we're bridging their science. And this is done through outreach and connecting with educators and putting our graduate students in the classroom. So it's this amazing project, and I got the amazing opportunity to do the project on mentoring. So I got to interview our fellows, our educators, our research mentors, and further understand how this program is influencing and changing our graduate students' experience in their grad school education, and hopefully impacting their career in a great way.
Next, we have another fan favorite at this conference. It was also very hard to get this poster because so many people were coming to their poster, but this is Natasha's poster. Natasha is studying Barbie, not really, but Barbie as an acronym for her work on exoplanets. Specifically, she's looking into biosignature identification on exo-Earths, which just means looking for signs of life on Earth-like exoplanets or planets outside of our solar system.
Hey everyone, so I'm Natasha. I am a PhD candidate, and I'm going to talk to you today about Barbie, which is going to inform us about how the Habitable Worlds Observatory, which is a super Hubble launching in the 2040s, is going to be able to characterize and identify exo-Earth candidates around other stars. That hasn't happened before, and we need to understand how we're going to do this before we build the telescope. So Barbie lets us explore large amounts of trade space using the Ken grids, no acronym, they're just Ken, and we can use this to inform the development of the Habitable Worlds Observatory, which, even though it has a base goal of helping exoplanets, is also going to be an incredibly high resolution telescope that is going to be helpful for all fields of astronomy. So please reach out, try to do some simulations, and clearly we like to have some ridiculous names involved. So bring yourself, bring your personality, let's get to work.
Next, we have Sarah, who in very simple terms is studying how the chemistry of rocks, like basalt, is altered through formation processes. The reason this is important is because we use the chemistry of rocks like basalt to tell us about the Earth's interior, like what Earth's mantle is made of and how it works. So understanding how rock chemistry can be altered after leaving the mantle is really important for improving our understanding of not only Earth's interior, but also the interior of other planets.
Hi, my name is Sarah Mount. I'm a PhD student at the University of Toronto. And what I'm studying is when you pick up a basalt and you measure the ratio of heavy to light isotopes in it, what does that signature represent? Does it represent the mantle reservoir it came from? Or was it changed by the different basalt forming processes like partial melting and fractional crystallization? And to get to the bottom of it, I'm doing experiments to try to understand how these isotopes preferentially partition between olivine and basaltic melt. It has big implications for how we interpret natural samples, which can tell us sometimes really big picture stuff about planetary formation. People use stable isotopes to compare our planet to chondrites, the moon, and Mars to try to unveil different events in their planetary formation. And this is kind of one of the first steps to making sure we're accurately interpreting the data we have from natural rocks.
Next, we have Esme, who is studying methane in caves, which I don't think I need to preface with anything because she does a great job.
Okay, methane is a really strong greenhouse gas, and we know that caves are places where methane is consumed. Caves are methane sinks, but we don't know exactly how that process works. We have three options. The first is bacteria that we know about and we have studied. The second is hydroxyl radicals, or super reactive chemical compounds. And the third are bacteria that are mysterious or unknown to us. So in my work, I determined that in caves, methane is oxidized really quickly in the entryways. However, when we look at the bacteria that we know about, the known methanotrophs that are here, we see that they aren't really confined to the entryways, and there aren't a lot of them. So I hypothesize that the methanotrophs, or the bacteria that we know about, are not responsible for methane consumption in Mammoth Cave. Instead, it might be something like those reactive chemical compounds or a new methanotroph or new bacteria that we haven't studied before. So I'm going back into the field soon to kind of try to solve this mystery a little bit more, but as for now, there's still a lot that we don't know. When we think about greenhouse gases, we think about budgets and things that are balanced. So if we can kind of understand one part of the budget or our cave, we might be able to understand the whole account or the whole budget better, which can help us in our efforts to fight climate change.
Next, we have Michael, who I want to emphasize is a high school student. I didn't do my first poster presentation at any sort of conference, let alone a huge one like this, until I was a fifth-year undergrad. So he's way ahead of the game, and I'm very proud to see high school students there. It's just really, really exciting. So Michael is studying plants that take heavy elements or contaminants like lead out of the soil to improve soil health and ecosystem health.
My poster is about heavy element uptake by hyperaccumulating plants. All over the United States, there's heavy elements all over the country. So if those elements are consumed, then there's a lot of damages that will happen to our organisms, like reproductive issues and neurological issues. So using hyperaccumulating plants, we can grow them in these contaminated areas and take lead out of the soil and other heavy elements, therefore having less problems to the health of United States citizens. So we found that these hyperaccumulating plants did end up having lead in them, and if you want to grow these hyperaccumulating plants, don't grow them in your environment.
Next, we have Allison, who is mapping access to healthy food.
Hi, I'm Allison from the Boston University School of Public Health. My project is comparing self-reported access to healthy food and geospatial access to healthy food. We're working with the Children's Health Watch cohort, which is an at-risk population of mother-child pairs from Boston, Minneapolis, and Little Rock. We took their addresses and assigned them to census tracts, and then took survey responses indicating whether they are food insecure or not. We then took the Deglaciation commercial database, and we took all of the grocery stores and calculated 10-minute walking buffers around those grocery stores, and we were able to see whether those census tracts had access to the grocery stores. We found that among families that do have geospatial access to at least one grocery store, around 30% of them still identify via the survey as food insecure, which is really worrisome. We also looked at historical grocery store data and found an almost 8% decrease from 2000 to 2020 with regards to access to grocery stores. So that's very concerning, but this is a pilot study, and we plan to expand it to other cities participating in the cohort, as well as other potential geospatial variables like socioeconomic status and access to vehicles.
Next, we have Sharil, who is studying manganese behavior during wildfires, which helps us better understand nutrient cycling during and after these fires.
So wildfires are increasing due to climate change, and several studies have been done to see how it affects many elements. But manganese is widely overlooked, even if it's important in several cycles, such as soil carbon cycling and organic matter decomposition. That's why for our study, we look at how fire transforms manganese during biomass burning to understand how manganese changes after burning, and then how it can interact with the soil after the burn. And this has implications on several processes that it's linked with, such as organic matter decomposition and nutrient cycling. Okay, so organic matter decomposition is linked to how carbon is stored or released in the forests. So we know that fire releases carbon, but after that, we want to know how will carbon behave in the burned ecosystem. So we want to understand that part. And the nutrient cycling aspect is important in the vegetation regrowth and ecosystem recovery of the forest after burning.
Next, we have Mara, who is studying critical source areas, which are portions of a landscape that contribute large amounts of pollutants to stream networks. So her work is improving our understanding of pollutant behavior, distribution, and migration in agricultural regions.
Hi, my name is Mara, and I'm from Penn State, and last summer I was able to go to Monash University in Australia in the Melbourne region. So I was looking for critical source areas for very flat landscapes. For critical source areas, you need two pieces of information: hydrological conductivity and nutrient flow paths. We didn't know if we could get the hydrological conductivity for a very flat landscape because I was working on a paper and the methods were based in Pennsylvania, a very hilly landscape. But using two methods of integration, I did a comparison of a farm about a half a mile scale over here, and turns out my hydrological flow paths were pretty accurate, as all the water converges here and the water travels from these points like that. Next, I was able to upscale to a 40-mile region over here to this LiDAR image. And this is a zoomed in version of this bigger map. And then this showed us the actual rivers. So we found out the hydrological conductivity could work for minimally sloped landscapes. And next summer, they're going to find the critical source area by combining it with the nutrient flow path information. So for farmers, they use a lot of fertilizers and other things. So they need to know where the parts of their farm can actually travel a lot more nutrients and non-point source pollution, and it can travel and cause a lot more damage than other areas in their farm.
Next, we have Anurup, who is improving our methods of finding life on other planets and moons by improving our methods of how we identify signatures of life on our own planet.
If there is life on Mars, it's likely living under the surface because the surface is just so hostile. And there are implications of that happening. So to know whether solar system is a habitable place, to know if there is life beyond Earth, this is super important, and this would lay the groundwork. For this work, we are trying to analyze subsurface fracture fluids. We are trying to understand how microbes function in nutrient-limited environments. And we are using DNA and RNA to study that. So if there is DNA, we can say the microbes are present, but if there is RNA, the microbes are active. So we can see through this plot that most of the microbes are present, but only a subset of them are active. We proved this using another approach that uses cellular resolution microscopy, and we can see the same results. So out of all these present cells, only these are active. Same for here. We are trying to understand the mechanism as to why that might be the case. So we are looking at DNA in these microbes to get a better idea. Thank you.
Next, we have Tyler, who is working to improve the accuracy of hurricane predictions.
So this is my work on seasonal hurricane prediction. I think seasonal hurricane prediction is very challenging to do. It's something that is quite important if we can give earlier, more accurate seasonal hurricane predictions. I think it can allow society as a whole to prepare in advance. And I think the big takeaway for me is that I think there is some ability to do these forecasts earlier in the year, but there's still quite a bit to do. These forecasts still aren't that accurate. You'll see they're like 0.5, 0.6, but initial hope that I think we can make improvement to deliver more accurate seasonal forecasts.
Next, we have Christy, who is helping develop methods to better track the progression of malaria-spreading mosquitoes through Africa. Her goal is to understand how climate change as well as seasonal variations are affecting the spread of these mosquitoes.
All right, so my name is Christy Weber, and I'm an atmospheric scientist from MITRE, which is an FFRDC. We were looking at the thermal suitability of the Anopheles stephensi mosquito. Why is this a particular concern? This is actually an Asian mosquito that has come to Africa. We're not exactly sure how, but this mosquito is prolific at spreading malaria. Djibouti has not seen a malaria outbreak since 1999, but starting in 2013, they started to see malaria. And the incidence of malaria has been increasing year after year since then. So we wanted to know how climate change is going to affect the range of this mosquito. And so what we've seen is that in the future, due to warming, the range of this mosquito is going to increase across parts of Africa. The mosquito has not been detected across the whole continent, but due to the way our world is interconnected through ports, shipping, any kind of transportation, it's pretty likely that someone on this part of Africa is going to be able to get here if they really need to. Mosquito doesn't need to rely on wind to get across this huge continent. So because of this, we built a dashboard that can look at all these different data sets, such as seaports, crowdsourced mosquito surveillance, climate change, and a number of other different sources to figure out, give you just a multimodal view of how the mosquito's range is changing, as well as looking at seasonal forecasts instead of climate change projections. So we want to know what the likelihood is for a rainier season 3 to 6 months from now. And that's it.
Next, we have Michaela, who is studying seaweed farming as a method of carbon sequestration to combat climate change.
My name is Michaela Sten, and I'm the University of California, Santa Barbara, and we're interested in how you can practically implement seaweed as a marine carbon dioxide removal strategy by putting large amounts of biomass on the sea floor, and what kinds of practical recommendations we can give to industry to implement related to how fast do you need to sink it, where in the ocean should you put this, how deep does it need to go, and how does this interact with climate change and how efficient is it?
Next, we have Elsa, who's studying how we can make better flood risk maps for Kenya. And this work can be applied to any flood risk area across the globe.
Yeah, so this project is about flooding in Kenya, and the region is being hit really hard by climate change. They've had a lot of drought, and then it kind of started raining and never stopped raining, and that has resulted in really huge floods the last 2 years. And so they really need flood risk maps, and they need them yesterday to respond to that situation. But the usual methods of developing flood risk maps are really expensive. So a lot of times you have to collect really high resolution data, and then you need a really experienced modeler and a lot of computational resources to do that. And so we're trying to just see what we can do with open data and open software and see if we can come up with something that will be useful. We have data from 4 different satellites about floods and where those are happening. You can kind of see the surface water there, precipitation, the topography. So this is the height above the nearest drainage. It's a really good indicator of where it's going to flood. And the vegetation. And all of that is going into a convolutional neural network, which is a type of model that takes images and then modifies them to create other images. These are some of our preliminary results. These are the kind of input layers here with precipitation and vegetation and topography. And then these are our observations. And then this is what the models predicted. And we think this is really promising because we're seeing that even with a relatively small amount of data and a relatively simple model, it's really picking up that the topography is very important, and we see that coming through in the final model. Moving forward, we're hoping to refine this, add more data and more complexity. And the great thing about using these global open remote sensing data sets is that you can do it anywhere on the planet. And so
that's really incredible.
Excited about.
Awesome. Thank you so much.
All right, so for the last few posters, I think the mic was not working correctly or turned down way too much, so it's a little harder to hear these presenters, but I really wanted to still try and include them in this video, so here are their presentations. The next one is Jiansu, who is studying carbon emissions from permafrost landscapes and the erosional processes that are contributing to these emissions.
Hi, I'm Jiansu Chulha. I'm interested in permafrost landscapes and how we can learn more about carbon emissions from the permafrost landscapes into our atmosphere. One of the important problems when doing that is understanding erosion that's going to ultimately mobilize that carbon. And what we're realizing is that permafrost itself, which is land that's frozen, has layers within it. And those layers can ultimately amplify the amount of erosion that we see. So here is a landscape called in Devon Island, which is high Canadian Arctic, where we're thinking that there are no layers within the permafrost. But then once you introduce layers, you can start having these features called active layer detachment slides. They're introducing water into the layer and lubricating it. And then if we move on and just imagine how that can happen over and over and over again, we can start forming these features called retrogressive thaw slumps, and that's what we're seeing here. These features are crazy. They can grow from 30 meters to 200 meters in 1 year. And so we're doing modeling to better understand why this is happening so quickly. And all of these have implications for communities who are living in permafrost landscapes and how they get mobilized into water pathways that might be impacting downstream ecosystems.
Next, we have Jackson, who is helping develop open-access databases and interactive online data visualization tools of coastal wetland data. This is really important because many scientific papers are not open access and they contain important data that should be accessible to everybody. So the people out there that are doing research like this to make data sets more accessible and more understandable are really doing very important work to actually make that data usable and applicable in, real world scenarios.
Coastal wetlands are a really, really important player in conversations about greenhouse gas inventories and capturing carbon. So they're really, really good at storing carbon. The Coastal Carbon Network is a coalition of researchers, coastal land managers, and decision makers that want to accelerate the pace of discovery in coastal carbon science. And we do that through providing access to data and synthesis opportunities and creating tools for insight, such as the Coastal Carbon Atlas, which is the interactive web application that we've developed to allow for users to explore, query, and download data from coastal wetlands all around the world. And we work individually with data producers who are wanting to contribute data to this resource and maintain transparency in that process. It also makes sure that we're elevating
elevating those researchers through the publication of their data, and also work on ways to communicate that data for insight, both at the state and national level.
And finally, we have Abby, who was unfortunately the hardest one to hear, so I had to cut out quite a bit of their presentation, but I still wanted to include it because she talks about paleoclimate, which is very close to my heart. Love paleoclimate. And so she's specifically studying how we can reconstruct past climates on Earth using tiny microfossils called radiolarians.
In the study, I specifically looked at the radiolarian microfossils at the site, and I was able to determine that radiolarian order richness was increasing throughout time, which complemented some of our past paleoclimate reconstruction into material, finding that there was increased precipitation, increased sea surface temperatures, and increased primary productivity. It's really important to study paleoclimate because as we're undergoing the changes of anthropogenic climate change, it's important to understand what is natural climate change, specifically for different organisms that live in the water, but also for human life. We need to know what is natural climate change.
So those are a tiny subset of the thousands of amazing presentations that were given at this conference. If you're interested in signing up for this or any other geoscience conference for 2025, I will have links down in the description box below that you can check out. Lastly, I want to just note that these are just excerpts from people's poster presentations. In reality, if you are a student that has a poster presentation coming up or you will in the future, these are more conversational. Typically, you'll give a very brief spiel of what your overview of your poster is about, like the people in this video did, but then it's followed up with questions and conversation from the person or people at your poster, and that it's way more, it's chill. So don't be all nervous. You have to do this formal presentation. This is just the way I had to do it for the video, but typically they're a lot more conversational. Anyway, thank you so much for watching. I hope this was helpful for some of you guys out there. And if you are not a student, I hope it was at least interesting to see some of the work that's being done. I found it incredibly interesting. And with that, I'll see you guys in the next one. Bye.